for coming at very much the end of the end, as it is. So I'd like to present work done by my two students, Karthik Nagareddy and H.K. Chan, that we do in collaboration with friends we have at the Naval Research Labs out in Washington, D.C. So the outlines, we'll talk about graphene, as I get to go first, and I get to explain why it's so exciting. We'll talk about epitaxial graphene, because that's a distinction between the work we do and the work that I believe will follow in the second talk. We'll then talk about functionalization. We'll show some materials analysis to show that is actually what we're doing. We'll then talk about the work we've done in organic chemical vapor deposition, and then we'll conclude. So graphene then is two-dimensional carbon. It's the building block of nanotubes and graphite. It's got the largest surface area at 2,700 square meters per gram. It has potentially got an ultra-high electron mobility. However, this is for graphene that is perfect and freestanding. As soon as you put it onto another material, this mobility drops. Epitaxial graphene is typically around the 5-10,000 mark. It's completely impermeable to all gas. And work by the guys at Manchester, led by Guy Novoselov, the guys who got the Nobel Prize, said it's possible to do single gas molecule detection. Sounds fantastic as a sensor. However, the response time was incredibly slow, and the recovery time was forever. Unless you annealed it at 150 degrees, you never got back to the baseline. So there are some challenges if we want to make this into a realistic sensor. So epitaxial graphene we get from thermal decomposition of silicon carbide. The big advantage of this is we have full wafer capability. The Scotch tape method generally produces much smaller fragments. So here's a Lee Heighton resistance map of a 4-inch silicon carbide wafer, and it's got something like a 2% resistance variation across 4 inches, and that's a fully processed one. That's a 3-inch wafer because it's last year's picture, and that is one atomic layer of graphene completely across a 3-inch wafer. So the big plus for us, well, we can stick it through standard silicon process technology, so we can go down the lab and do things as we would normally do, and we can integrate it with existing silicon carbide circuitry. So here is a model of the silicon carbide underneath. The graphene layer is actually the one above this. This is the interface layer, and you can see that we have chemical bonding between the silicon carbide and this interface layer, and then there's further bonding into the graphene above. That is a big difference in comparison to what you get with the Scotch tape material. Sample preparation, we put it through a hydrogen etch to completely clean, flatten the surface. This is what the surface of silicon carbide looks like. These are the step edges that result from the epitaxial growth. We can't grow it perfectly on axis. It doesn't work. We have to tilt the wafer slightly. So we get these step edges, and these are atomic crystal planes. And after the growth of the graphene, which in this case is under argon at 1540 degrees, we get a single layer of graphene on the flat bits, and then like the stair carpet at home, we get a couple of layers as we go over the step edge. It's slightly bumped and raised as we go down the steps. All our sensors are fabricated so that they actually look along these terraces. If we go across the step edges, it gets a lot more complicated. The oxygen functionalization process is shown here. So it's a sheet plasma, which gives us a very low incident energy of the oxygen. Because graphene is all surface, it's very, very easy to damage the surface. And one of the critical steps of the work that we're reporting actually is in the development of the process to enable this. So there are two possibilities. The first one, favored by the materials people who grow it, is we grow the graphene, we then functionalize it, and they give it to the sensor people. Well, that doesn't really work, because when we put the contacts down, we form titanium dioxide, and the titanium dioxide here gives us a much higher resistance, so functionalized first, fabricated next. So these are TLM plots, and it also gives us far higher noise. Now, one of the big challenges in sensors is your noise floor. So our basic noise is right down here, and this is sort of like on the edge of beating everybody else's at the moment. But if we functionalize first, it goes up by 6 orders of magnitude. So one of the things we did was we built the sensor, and then we functionalized. Seems obvious, but the process development required to keep this surface perfectly clean so that we can functionalize whilst we go through all these horrible dirty processes like photolithography and metal deposition and etch is actually quite a challenge. As soon as you put photoresist onto graphene, it destroys the surface. And as soon as you destroy the surface, it's very difficult to recover. So in this case, we get a far lower resistance, as what we have here is predominantly a resistive sensor. Having this much lower resistance is going to give us far better sensitivity, and we've got a much lower noise. So XPS, well, this is our as grown, so you can see the silicon carbide, which is the bulk layer underneath. We have sp2 carbon-carbon bonds here, and we've got the interfacial layer, which is strained, and so it's distorted. After we've had it do the option functionalization, so this is 2.5% coverage, we get CO bond and COO bond here. And this allows us to realize that we've actually functionalized the surface nicely, and it hasn't actually got through, so we haven't got any defects. It hasn't got through, we haven't got any silicon dioxide layers either. We also did some Raman analysis. So as grown, we have a completely insignificant D peak, which shows that the material is very high quality. After functionalization, we do have a D peak here. This is really the sp3 characteristics of the carbon. It's an allowed Raman mode for sp3. And really it shows the disorder peak. So it changes to about 0.35, which is still pretty low. Interestingly, here, we don't see the mobility drop. Normally, if you have a D peak, your mobility goes down significantly. However, for the 25 devices we've tested, it changes from 1,000 to 980. So this is obviously still good material even after we functionalized. So in terms of solvent sensor, here's our device. We expose it to analytes at about 0.1% in standard laboratory air in Newcastle. Air is the pink line, and we get either an enhancement in current or a decrement in current, depending on which type of solvent we put on it. And we generally show them then as delta R over R. Two things, polar protic material, so these are hydrogen donors. We get a response, then when we remove it, it goes back to 0. And then here on this side, we see the same thing. These are polar aprotic, so they're polar materials, but they don't have a hydrogen donating ability. Note here that in 75 or 80 seconds, we've got saturation for 2 of these. NMP hasn't. We also get recovery. This is something that a lot of graphene-based sensors do not get. So response and recovery, well, if we take a comparison between non-functionalized blue and the oxygen functionalized, 2 things to see. 1, we see an enhanced response. 2, we get a full recovery. So that's hydrogen peroxide, that's polar protic, and on this side is dimethyl anhydride, I think it is. Again, we see a larger response, and we see a full recovery. So by changing the surface of our material, we actually now can recover, as well as having a larger response. We looked at dipole moment. Well, our original works, this is on the non-functionalized material. Water has a dipole moment of about 1.8, and because we don't control the humidity in the lab very well, we looked at dipole moments above those of water, and we see what we considered to be an exponential behavior. We could have a linear fit. It depends on how good a curve you want. This is the same data taken on the same day for functionalized material. Notice the response here at 44% is higher than that at 28. But we see the same trend. The dipole moment increases, the response from our sensor increases. This is because when we put a molecule on the top, it changes the amount of charge in the graphene, and so it changes the resistance, and that's our idea of how the thing works. To try and understand this a little better, we use 1/f noise, because this is quite a sensitive way of looking at the behavior of our layer. So here is the noise. When we add a chemical to the top, we've changed the doping density in the layer. According to the Hooger model, that explains that we should see a shift in the noise, which we do. So we're happy with that. This one then is the functionalized one. Again, we see an increase in noise here at moderate frequency. These spikes are UK mains, they're 50 Hertz, and we tried to cut them out, and it doesn't always work. However, this bit shows something slightly different. Down here, we see a 1/f squared behavior once we get below 25 Hertz, whereas this here is 1/f, as it is here for the whole frequency range. This is something different. This is indicative of a generation recombination mechanism that's been published before, and we think this comes back to detection. However, these are very long time periods. We're talking, things with a time period of 100 milliseconds to a second. It has to come out to chemical kinetics. We think it's the absorption and desorption of material on the surface. We haven't got to the bottom of this because actually this red line here was Thursday last week. So we're going to have to leave that one hanging at the moment. We think that's what's driving the detection, but we're not quite sure. So to conclude, well, for the first time we've shown a significant improvement in response of a graphene sensor. We haven't degraded the electrical characteristics at all. Functionalization after fabrication offers the greatest response, but also at the same time offers by far the greatest challenge in processing. So those of us who work at the sensor end think it's great, and the lads in the clean room are less happy. The magnitude and direction of response is a unique fingerprint. We've identified that the dipole moment allows you to identify uniquely which materials you've got. The next challenge will be mixtures, just in case anybody's thinking of that one. And we actually now have the ability to do different functionalization. This is all oxygen. We have process recipes for fluorine and amine groups because we're looking at moving into bio sensors in the future. The sensors themselves are stable to 400 degrees, although we can't detect solvents at that temperature. And thank you very much. I'll attempt to answer any questions you might have.